This is Knowledge Engineering with Semantic Web Technologies, lecture number 6, Knowledge Engineering. And this is also part number 6 of lecture 6, Semantic Search. Okay, in this part of the lecture, we want to look at semantic search and how semantic technologies might help to improve traditional search technology. So for that, let's first take a look at search engines. Here, for example, we have Google. Of course, Google is anything else but a traditional search engine, because also nowadays lots of semantic technologies are already included in the processing and in, of course, the technology of a search engine like that. But nevertheless, let's have a look. So what I did here is I was looking for Jules Verne, and what you see what Google does, for example, when I'm typing, or right in the moment when I'm typing, I have a choice of selections available. What could I mean with what I'm writing? So for example, you have an auto-completion system that tries to think ahead of you and help you with your search query. And by the time you are typing, also the first results are created. So let's imagine here I'm looking for Jules Verne, and you know, first the knowledge graph, this is the part on the right side here of the screen, detects the entity Jules Verne in the text. So this is the first entity mapping here already for the most likely entity that has been detected in my search phrase. But if you take a closer look here at the search results, of course, you will find information about the author, Jules Verne. But here, number 4, again, you have a restaurant which is called Jules Verne and which is on the top of the Eiffel Tower, for example. And this is named after the author. But you see here again, you have the same difficulty that we also had when we did named entity resolution. You have ambiguity to take into consideration. So in the news, for example, here is a ship or a boat which is named Jules Verne. This could also be meant by my search query. So it's difficult for the search engine to decide what I have really in mind if I'm only operating on text. So this, of course, is a problem. Let's have a look how it is with the other search engines. So as a next example, I took Bing. Bing, for example, here I was logged in the system, so therefore the choices that I presented, they are in German here for the auto-completion. But nevertheless, if you look closer at the results here, you see, for example, information about the author, Jules Verne, but you also see, for example, a school which is named after Jules Verne, and you will find a club and a restaurant with the same name. So also Bing has to deal with this disambiguation problem and does not in advance know what you are meaning by your search term. And also consider here, Bing also displays something like a knowledge graph. So it has detected an entity and you will be shown information about the most likely entity, which is Jules Verne. So the final example, I tried also my search at a Chinese search engine, here at the most famous one, at Baidu. And what you see here, again, of course, Jules Verne has been detected. I have lots of interesting, so here, of course, somehow other kind of suggestions. So these kind of search suggestions sometimes are created simply from the search logs, and you see here what has been queried most. So for example, for Jules Verne, the most quoted query would be Jules Verne was called father. That's interesting. So possibly he was called father of science fiction or something like that. It's also nice, Jules Verne in his and Jules Verne Phileas Fogg, which then is, I guess, referring to one of his novels called In 80 Days Around the World. So you see here definitely also entity Jules Verne, but you see also here below the box, you see here an advertisement for Le Jules Verne, and this is the restaurant Jules Verne that is here also referring to. So to get a better impression of that, I have of course translated this page on the next page of the slide. You can see it here, and you see here in English written what is the original Chinese here, and also there is some kind of a knowledge graph which has been used for suggesting other kind of searches. So for this one, similar searches, for example, are presented. So Jules Verne here, for example, is considered a children's literature writer. And if you are interested in Jules Verne, probably you are also interested in Nobel Prize in literature writers. So Jules Verne never was a Nobel Prize winner, but never take this into account. So at least here also these these search engines are not only text-based, of course, they are also considering the semantics today. But nevertheless, the problem is if you do not have sufficient context information, it's difficult to decide what is really the meaning of this information. So traditionally, all of these search engines, they are text-based search engines, and usually they follow the standard traditional retrieval paradigm. So how does this standard information retrieval paradigm, I mean simplified, work? So you have on the right hand here a set of documents, which at Google or at Bing would be the set of all available or all crawled web documents. And on the other hand, you would have a set of queries. And what you do with both, you bring them in a form that both can be compared somehow. So with a set of document, you do an indexing processing. So you try to develop an index in some kind of language which can be compared then with the query or the processed query. And then what is in the intersection of the index and the query is your result. And this result usually is based on a kind of similarity matching. And if you're considering only text, this similarity, of course, is string similarity. And therefore, of course, the same text or the identical text will be found first. And then, of course, text that is somehow similar. So where the distance between the two strings is somehow then later on increasing. But we know, of course, if you're only considering text, which is not really unambiguous, so which is not really unique, you might become or you might have difficulties with finding the correct result and also finding the complete result. So, yeah. How does it work? So usually you give here a search query and your search term is looked up in the search index, and your original document then provides keywords within the indexing process, and both of them are then compared in the search engine, search index, and then the resulting document which provides a hit will be presented to the one who is retrieving that document. But usually we know we have ambiguity. So if you have missing context and if you are looking, for example, for Jaguar, the search engine has no idea whether you are looking for the cat or whether you are looking for the car. You only can distinguish these if you provide additional information. And this, of course, might be a problem. So to solve these issues or to cope with these issues of ambiguity of natural language, you must definitely include semantic information which helps you to identify your exact information needs. And it's getting more complicated if you try to consider implicit information. So we have talked about that in the very beginning of our lecture. So in the example that you see here, it's quite difficult to determine which kind of Heisenberg really is meant in that phrase and what was the current situation and the context and why is it standing here. So it's difficult to interpret, it's hidden somewhere, and you need some expert knowledge, some situation knowledge of the time when exactly this information was created to know what kind of implicit hidden information is below the surface of what you are seeing here. So this is difficult to interpret because of implicit and not explicit available information. So there comes semantic search to help you in that situation. What is it, semantic search? So usually your documents will be annotated. So you have annotations of your traditional text-based metadata with explicit semantics. So which means, for example, with semantic entities. We have seen this in entity resolution. Just imagine you have a natural language text, and all of these entities that are somehow represented in the text, they are annotated with a semantic entity which comes from a knowledge base. And this process, of course, is unique. So it's a unique mapping. And therefore also the entities in the knowledge base, they are also unique. So what you do here is you try somehow to avoid this problem of ambiguity within language, at least in your indexing process, by making it unique in that annotation process with explicit semantics. Then you would be able to perform something which is called entity-based information retrieval. So it's not text-based or keyword-based anymore. Then it's based on the semantic entities you are considering. And this is a nice thing because if your text is in any language available. So consider an arbitrary language and it's annotated with entities from a knowledge base. It's language independent because, for example, a specific person exists in many knowledge bases and you can provide names in any kind of language of that person or of that entity within your knowledge base. So this would be a way to provide language independent information for retrieval, which of course is a huge benefit. And of course, you could also make use of the entire knowledge in that underlying knowledge base. For example, you could find out about content-based similarities among entities. You could determine, if you have annotations of two different entities, how similar are these entities with each other? And is this somehow relevant for the search, for example, or to answer a search? So this would be right interesting. And not only consider similarities, also consider other kind of relationships between these entities. Because, for example, if I'm looking for tennis players and I specify my query tennis player, then I might be also interested in information about specific tennis players, like, for example, Boris Becker. And if you consider a website where Boris Becker is mentioned, but nowhere is the word tennis or tennis player mentioned, we don't know in the document that this Boris Becker really is a tennis player. For that, we would need a semantic annotation which identifies him as Boris Becker, who is member of the class tennis players, to answer that query. So this would be kind of a relationship which is important and which would also provide or help us to provide a more complete answer for our retrieval, for our search engine. So this is something where semantic search really can help. And of course, it produces with these semantic annotations some kind of interoperable metadata. This is, of course, something nice. And the metadata that you use usually here in these search engines is content-based description. So, for example, text is annotated with mappings of entities that are linguistically retrieved or identified within the text and with a specific resource in a knowledge base. On the other hand, you also can have structural or technical descriptions that can be used for retrieval. And another purpose besides, let's say, the plain retrieval to display one list of result like you are used to get the result in the standard search engines today, you could also use this information for content-based navigation and result filtering. So you could filter your result based on so-called search facets. You all know what search facets are, so usually these are kind of filters that filter your result. You all know that, for example, in the image search at a search engine, you often have the possibility to filter for images that have a specific size or that have specific content. For example, you can distinguish between photographies and you can distinguish between, let's say, sketches and something like that. So this is often possible. So this would be a search facet that filters your result. And these filters could also be based on content of the document, not only on technical or structural things, really on the content. So this would enable then content-based navigation. So these are things that are tried to being achieved with semantic search. So if you compare semantic search and keyword-based search, where are the benefits that you have? So first, you could apply it for so-called query string refinement. So what you could do is you could somehow enable more precise and more complete search results. So how you implement this query string refinement then, of course, is another thing. So one possibility would be some kind of auto-completion where, for example, if I give the information Jules Verne, I would have then the possibility to distinguish, do I mean the author, the restaurant, the ship, or anything else? So this would be a selection process, a refinement process for my query string, which is based on the semantic annotation of the entity that has been identified within the query string. Another thing I could do is, for example, cross-referencing. So with relations and cross-references among my entities in the knowledge base, this would enable to complement my search results with additional associated or similar information. So this would be something interesting to get more results, to get more complete results, simply based on information that can be sketched or that can be taken from my knowledge base. I could also somehow enable a fuzzy kind of search. Simply, so consider, for example, small knowledge bases or small document corpus. So if you are looking in a small archive for a specific term, a specific query term, it might happen that you don't get any result. So for this, for example, simply because this entity never occurs in one of the documents. But for this, you would be interested in nearby results. So what is really close by? So instead of delivering no answer, I could give you the closest possible answer. This would be kind of a fuzzy search that can be enabled with semantic technologies simply by taking into account semantic similarities among entities. And another very interesting thing, and also an ongoing topic of research, is the so-called exploratory search. So with exploratory search, this enables you to visualize and to navigate your search space, to really look into your search space on paths, to explore your search space on different paths that can be created on the flight, for example. So this is somehow like window shopping or like browsing through a catalog, but you are guided somehow. And the guide usually determines the direction to go, considering your preferences, for example. And of course, you could use this information for reasoning to enable also to complement existing search results with implicitly given information. So this was the very last example with this Heisenberg we were talking about. So for this, you have to establish a reasoning process which comes up with a correct solution. So at least to complement your standard solution with that kind of solution. So this would be all areas or problems that can be addressed with the help of semantic technologies, and that of course are somehow part of that semantic search process. Let's have a look at entity-based search first. So entity-based search, for this I would annotate my document corpus with semantic entities, and of course also I would annotate or try to analyze my search query accordingly. So try to imagine the following search. I look for Armstrong on the moon. What I do here in that search is I try to find out which are the entities, the named entities referred to in my search. And I could, for example, identify Armstrong, which is Neil Armstrong here, because I have the moon as a reference. And of course, I could identify the moon as a celestial body. So these are the two entities that have been identified within my query. On the back-end side, I also have here my search engine, and of course the search engine must have, during the indexing process, must have performed a named entity resolution on the text documents that are available. And for this, for example, in the example you see here, we have a document that has been labeled, for example, or annotated with Neil Armstrong for a string that has been found here, the first man of the moon, which is mapped in a knowledge base to here DBpedia entity Neil Armstrong. And we have also the moon, which then is mapped to the moon as a celestial body. And if you do then a simple entity matching, which means you consider only identical entities in your query and in your index term, you might directly find that document. Then, of course, you might find many documents which contain these two entities, and then you have, of course, also to consider which should be then the order of the documents, of the result documents. So what should then be a criteria for ordering these things and to present the best, of course, search results on the top of your result list. And this, of course, can be achieved with similar technology that is used in text-based search engines. So there are, for example, this term frequency, indirect document frequency approaches. You can look this up in information retrieval, TF-IDF, which can be simply adapted, for example, for also ordering semantic search results. So this is simple entity matching. But of course, you can also take into account, we said that, relationships among these entities. And then it's getting more interesting. So for example, consider another document that we see here. So we have here a document on the second man on the moon, and probably our search engine cannot map the second man on the moon, but it can definitely map the moon here. And it finds also another entity here in the text, and this entity is Buzz Aldrin, which was, we know that, the second man on the moon, of course. And then you could consider, for example, similarity of the found entities in your document and the entities in your search query. And you will find out that between Neil Armstrong and Buzz Aldrin, there are lots of similarities. So you have to consider semantic similarity. When are two objects semantically similar? So two entities are considered semantically similar if they share many properties and property values, or if they share many properties with similar values, then they are considered as being similar. So this would be, for example, a similarity-based entity matching. What you would do in your search engine, of course, you would take first, or in first place, the simple entity mappings or simple entity matchings, and then you would consider similarity-based entity matching, because they are a little bit farther away from your original search goal, but nevertheless they might be related. So for completeness, you should also consider this. And we have a third possibility, which are relationship-based entity matchings. So here consider, for example, again our document, The Second Man on the Moon, and we consider the following entity resolutions we have found here. First, we have found Moon, we have found astronaut, and we have found Apollo 11 as entities. And then you could consider what are, so one entity, of course, so the Moon is mapped directly, so this is a simple entity match, but we have astronaut and Apollo 11. And now you have to consider the relationship between these entities and the other entity in your search, which is here Armstrong. And so between Neil Armstrong and astronaut and Apollo 11, there are, of course, qualified relationships. So Neil Armstrong was on the Apollo 11 mission, and of course Neil Armstrong is of type astronaut. So therefore, there is some similarity. And not only similarity, of course, there is a relationship between them. And therefore, this document might also be related to your answer. It's not as closely related as if you really consider the same, or if you would really find the same entities in your text, but it's the same as the similarity-based entity matching. It complements your search with nearby closely related results. And this would also be then an interesting result for semantic search. So these are three possibilities that you have to consider for your results in semantic search if you consider entity-based search. In difference to this approach, you could for your search also consider entities as a query input. So this means that you do not type a text which is then interpreted automatically, where a named entity resolution has been carried out automatically. You could select, for example, the entity that you have in mind in the same way like you do this with auto-completion. So we have here an example of a system which, when you, for example, type Armstrong, can select among persons, places, things, or events that are labeled with Armstrong, and then you can directly click on the entity you have in mind, and then a search is carried out exactly with that entity. So you can look this up at refer.cx. We will give you the link in the page with the lecture materials. Based on that, or on top of that, this entity-based annotation and this entity-based search, we have, for example, implemented a small system which also allows you to do information exploration. Here, for example, in a blog that we are currently providing, this is a blog at yovisto.com. For example, all of the entities, or many of the entities in the blog articles, they are annotated. They are annotated with semantic entities. And what you can do with it is really amazing. Simply, you can, for example, display the information content of that article in the blog, of that blog post. You can, for example, display in some kind of a graph the entities and how they are related with each other. So here you have the example of Werner von Braun. He's a famous engineer responsible for the Apollo 11, the mission to the moon and all of that. And here you can see, for example, the relationship to his father, Magnus von Braun, for example, or that he comes from Germany and stuff like that. And you see here all the relations between the entities fields with their properties that come, of course, from the knowledge base. So this is something to make clear or to enable navigation and also to visualize the information, and of course a first step into information exploration. So you can try it out at that web address. Which gives us way to the next part of our lecture, and there we want to go from simple semantic search to a so-called exploratory search, where we try to explore the search space that is available further.